Dr. Incognito. In this video, we're going to study the ratio and root tests. So the ratio and root tests. But first, let's take a look back at the geometric series. Geometric series has the form summation AR to the n equals 0 to infinity, and that would be A plus AR plus AR squared, etc. If we want to find the ratio of this series, the common ratio R, it would be any term, I'll call it the n plus first term, divided by the nth term. Another way to find the common ratio, if you factor the A out, and or just say A is 1, then 1 plus R squared plus R cubed, etc. The ratio is the nth root of the nth term. That would be the nth root of R to the n. So the ratio and root tests are going to be used for series that are almost geometric, and they're going to be based on the principle of trying to find the common ratio R by either this ratio or by this root. So in the ratio test, we're given a series and we compute the ratio an plus 1 divided by an. That would be the n plus first term divided by the nth term. And we take the absolute value of this and then the limit as n goes to infinity. And suppose we get some number L out of this ratio, limit of the ratio, then if L is less than 1, the series that's given converges. In fact, it converges absolutely. If L is greater than 1, then the series will diverge. And unfortunately, if L is equal to 1, then we get no conclusion from the ratio test. If L equals 1, then no conclusion. In fact, if we use the ratio test on a p-series, for any p, we will get a limit of 1, and some p-series converge, and some p-series diverge. So we don't want to use the ratio test on a p-series, or even something that looks like a p-series. We want to use the ratio and the root tests on things that look like geometric series. So as an example, let's take the summation n equals 1 to infinity of n squared over 2 to the n. N squared over 2 to the n. So if the n squared were just 1, the summation of 1 over 2 to the n, this would be geometric with common ratio 1/2. Well, when n is very large, 2 to the n is going to be much, much larger than n squared. So the n squared here is insignificant in comparison to the 2 to the n. And so this is going to behave like a geometric series with ratio 1/2. To see that, we'll use the ratio test, and we will see that this limit is 1/2. 1/2 is less than 1, and so the series will converge. So first, let's just analyze a sub n plus 1. A sub n plus 1 is n plus 1 squared over 2 to the n plus 1. Everywhere we see an n, we replace it by n plus 1, and sometimes parentheses are helpful. So now let's do the ratio test. The limit as n goes to infinity of the absolute value of an plus 1 over an is an plus 1 is here, n plus 1 squared over 2 to the n plus 1. And then I'm going to think of this as being a sub n plus 1 times the reciprocal of an. So I'm not going to write fraction over fraction. I'm going to write this fraction times the reciprocal of this fraction. So a sub n is what we see here. So times the reciprocal of that puts 2 to the n on the top and n squared on the bottom. So we want the limit of the absolute value of the product of these two fractions. This is a sub n plus 1. And this one is the reciprocal of an. So first we'll deal with the absolute values. All four of these factors are positive, so we don't need the absolute values here at all. Then what I want to do is a little bit of organizing. There's two types of fractions here. There's two types of factors in these fractions. There's the n to a power, n plus 1 to a power, the squares, and then there's the exponentials. So the power functions, n squared and n plus 1 squared, and the exponentials, 2 to the n and 2 to the n plus 1. So I want to group them together. So I have n plus 1 squared over n squared times 2 to the n over 2 to the n plus 1. So just a little bit of bookkeeping. And now, a little bit of rewriting. N plus 1 quantity squared over n squared. I'm going to rewrite that as one big square. N plus 1 over n quantity squared. And then the exponentials are going to cancel significantly. The general rule being, if you have x to the n over x to the m, you can subtract exponents. So here, if we do that, if we subtract the top exponent minus the bottom exponent, we'll get negative 1. So 2 to the negative 1, that's a half. And of course, we can see that another way. 2 to the n means we have 2 times 2 times 2, n times. And here on the bottom we have 2 times 2 times 2, n plus 1 times. So there's one extra 2, one extra factor of 2 in the denominator. So there it is after canceling. And now this limit, the limit here is the quantity in the parentheses is headed to 1. N plus 1 over n is headed to 1, looking at the ratio of the lead coefficients. And then that's squared times a half is a constant. So this is 1 times a half. It's a half, as promised at the beginning of the example. And then our conclusion structure here, our L is less than 1. This is less than 1. And so the series converges. The series converges by the ratio test. And we could say that it converges absolutely, but here we have a series of positive terms. So the extra modifier here is not really useful when you're dealing with a series of positive terms. I'd like to do another example of the ratio test. The ratio test is very useful in problems involving factorials. So let's look at the summation n equals 1 to infinity of n squared times 2 to the n over n factorial. And let's throw in a negative 1 to the n. Let's make it alternating. So that now, if we do get convergence, the absolute convergence, we'll be saying something. So a sub n plus 1 here, a sub n plus 1 is negative 1 to the n plus 1 times n plus 1 squared times 2 to the n plus 1 divided by n plus 1 factorial. And the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is equal to the limit of negative 1 to the n plus 1, n plus 1 squared, 2 to the n plus 1 over n plus 1 factorial, and then times the reciprocal of a sub n here. The reciprocal of a sub n, I'll put the negative 1 to the n on the bottom, and then we have n squared times 2 to the n and n factorial on the top. Now the first point I'd like to make is that the absolute value of negative 1 to any power is 1. So in calculating the absolute value here, the negative 1 to the n plus 1 and the negative 1 to the n are just both going to give me 1, and I'm multiplying them, they're being multiplied by other things. We're multiplying them to other things, so I will just not write it. 1 times x is x. So we get here equals limit as n goes to infinity, and doing the bookkeeping as well, I have an n plus 1 squared on the top, and I have an n squared on the bottom. Those are my powers. And then I have some exponentials. I have 2 to the n plus 1 on the top, and 2 to the n on the bottom. And then I have my factorials. N factorial on the top, and n plus 1 factorial on the bottom. So I want to take the limit of the product of these three fractions. So I've already handled the first two fractions in the last example. The new thing here is the factorials. So the limit as n goes to infinity. The first one is n plus 1 over n quantity squared. The second one, actually, it's the reciprocal of what we had in the last example. In the last example, the 2 to the n plus 1 was on the bottom, the 2 to the n was on the top. So after canceling, we got half. Here it's going to be 2. And now, n factorial over n plus 1 factorial is going to simplify to 1 over n plus 1. And the limit is 1 squared times 2 times 0. As n goes to infinity, the first fraction goes to 1 squared. The second one goes to 2, it's constant. And the third one, the denominator is going to infinity. So 1 over infinity, that's going to give us a 0. So the answer here is 0. And since 0 is less than 1, we have the conclusion of absolute convergence. The original series over here, the series converges absolutely.